Three talks today. The first speaker is Luiz Carvalho from University of Edinburgh. Actually, I have to make the announcement that the original presenter has been changed from Leonardo Bastos to Luiz. Okay, so he's going to be speaking on the choice of weights for logarithmic pooling of probability distributions.
Thank you. Hello. Thanks everyone for coming. I know after coffee breaks always nasty time. So I'm Luiz. Leo was originally scheduled to talk, but I stole his place. So just a quick chat about the other collaborators. Daniel is a mathematician at Fiocruz, at the Scientific Computing Program. And Flavio is a professor at the School of Applied Mathematics. And of course, Leo is that beautiful chap over there. Well, today I'll be talking about the choice of weights in logarithm pooling of probability distributions, but we'll get to what exactly that means in a minute. Shall we? Slight technical problem. Yeah, the computer is slightly slow, but it'll get to it, I suppose. Yeah. Yeah. Okay, so what exactly is logarithm pooling? Oh, God. Okay, so first of all, before I bore you with the mathematical details, let's get to some motivation on why we do this. So we are interested in obtaining coherent group opinions. When you have a set of experts with opinions on a particular quantity, we are interested in combining those opinions into a coherent pool. But in this particular setting, oh. All right, there you go. Okay, so in this particular setting, what we are interested in is when the experts elicit their opinions in the form of proper probability distributions. So logarithm pooling is a way of combining those distributions that enjoys many nice properties, many nice mathematical properties. I will not discuss them here, but I urge you to look at our manuscript that I'll make available shortly after to look at some of these interesting properties. So it has applications in many different fields of science, but it has a slight caveat that it depends on a set of weights to be given to each expert. And that is what we are going to try to address here. So let's get some definition and notation out of the way. So for a set of probability distributions, proper probability distributions, that represent a set of experts, or the opinions of a set of experts, we will have a vector of weights called alpha, and they have to attain to certain properties. But that, equation 1, shows you how we combine the densities, how we combine the distributions. So in a very famous paper in JASA in 2000, Poole and Raftery prove that for any two proper distributions you can combine, and you will always be able to normalize this density. So you will always be able to get a proper distribution, and we extend that theorem to more than two densities. So we can be looking potentially at very large sets of opinions here. Now, there are plenty of ways where on how you can choose this weight. So what we want here, what we're going to try to discuss, is how we can choose the weights using information that is encoded in the distributions themselves, rather than externally assigning the weights. So the first approach we propose is to maximize the entropy of the combined distribution. So this is an optimization problem. What we want is to find a vector alpha that will maximize the entropy of the prior. Well, why would you want to do that? You can do this because you may want a distribution that is maximally uninformative, that has the broadest possible. But one caveat with this approach is it's quite easy to implement, and it actually has a very nice closed form for the exponential family, which is a very broad class of distributions. But the slight caveat with this is that you're not guaranteed to find a unique solution because it's not a convex problem. And also, it can very easily drift to what we call trivial solutions. That is, you assign weight 1 to one expert or one distribution and give everybody else 0. And that may or may not be desirable depending on your goals. Let's wait for the passing. Oh, sorry. Okay. So the second thing you can do is you can minimize the divergence, the disagreement. I'm sorry for that. It will pass, I promise. Come on. Okay. So what you can do is you can minimize the disagreement between each individual opinion and the pooled opinion, and that's also an optimization problem. But in this case, rather than maximizing entropy, what we are doing is we are minimizing that loss function over there, which is just the sum of Kullback-Leibler divergences between each density and the pool. And contrary to the above, to the previous one, this one actually allows for a unique solution. So you're guaranteed to find a unique alpha that minimizes the loss function. And I hope this first two are sort of intuitive to everyone. What is the motivation behind each one. And the third thing you can do is, if you don't want to do these optimization problems, what you can do is assign a prior on the weights. We are Bayesians after all, so we like to put priors on things. And I think you will agree with me that two interesting options for this are the Dirichlet prior, that nice face over there, and a logistic normal prior, which is just a normalized sum of the exponential of normal distributions, that is log normal distributions. And the second parameterization may be interesting if you want to have slightly more fine control over your priors, because you can assume a flat prior on the weights, or you can elicit these distributions to account for the uncertainty you have on the weights. So rather than fixing a set of weights, you can assign a prior distribution and then take into account your uncertainty on the weights. And that's the advantage, I think, of this approach. But the caveat is, well, we really don't know, to this point, whether the results are consistent, because we really don't know how this behaves, how this whole thing behaves. And, well, the second one, the logistic normal prior, will hardly ever allow for analytical solutions. In fact, if you try to look at the full prior, the full pool distribution, not even the Dirichlet prior will allow for analytical solutions, and you may be interested in that. Now, let's look at a small application. That is, imagine you're interested in a probability, the probability of failure of a particular item, and you then call on a set of experts to give you their opinions on whether this item is going to fail, or what's the probability of failure. And, well, of course, I think a natural thing to do is to put a beta prior on this quantity beta, this probability. And as I said, using a beta distribution has the nice property that the pool distribution will have a nice looking analytical form, and also you'll be able to very easily compute the KL divergence and the entropy. So you can very efficiently sample this within MCMC. So we're going to be looking at the example from Chavuk and Martz, where they call on the experts to give priors, and then they observe 9 successes out of 10 trials. So one thing we're going to do here, for lack of a better performance assessment, is to look at the marginal likelihoods of each prior, and also look at the marginal likelihoods of the combined prior under the 3 approaches we've been talking about. Okay, so this little figure is, on the top panel, you can see the priors that were given by each expert. And in the bottom panel, we have many lines, but we have basically the priors and posteriors using all of the approaches we've been talking so far. And the results are not really, they don't stand out clearly, but you can see that the hierarchical priors, they assign higher density to the sort of true value, the value that was observed on the experiment. And, but you can't really tell the difference between the Dirichlet prior and the ESP normal prior. And this may be for a variety of reasons. Maybe because the problem is rather too simple. And here you can see the weights we obtain using the approaches we've been talking about. So the hierarchical prior here is the Dirichlet prior, a flat Dirichlet prior. And you can see, as I said before, the maximum entropy approach gives you what we would call a trivial solution, where it assigns all of the weight to one expert, one distribution, and gives everybody else 0, which may or may not be desirable. If most of your experts are not really experts, they're not really good, maybe that's an acceptable solution, but maybe not. The KL divergence doesn't do this, and let's see if we can show this. Yes. So, yeah, it really achieves a nice consensus between the density. So with only those 2 weights, you create a distribution that reflects the opinion of almost everybody else. On the second table, you can see the marginal likelihoods, the integrated likelihoods for the experts on the left panel and the pooled prior under different approaches in the right panel. And in this example, we can't really tell much of a difference between the approaches, but I really don't know if this is because the example is rather simple, because they really are not that different. Maybe if we had a more complicated example, we could see more difference between the approaches. So as a partial sum up, we can say, well, the results are not decisive yet. And the Dirichlet approach would seem the most appropriate from a Bayesian point of view. I think if I asked every single one of you which prior you would put on the weights, you would say a Dirichlet prior, because we know a lot of results for this prior, and we know how to deal with it. We know how to elicit it. But what's pending from this analysis is a nice prior sensitivity analysis. We don't know how our approach is sensitive to the initial hierarchical prior. So now I'm going to cheat you a little bit, because I'm going to switch, and I'm not going to talk directly about the choice of weights, but I'm going to talk about something that I think is interesting in the same context. So now what I want you to imagine is you have a set of distributions on a quantity theta, but you're really interested in a quantity y that is connected to theta through a model M. And so that's what I'm saying in the slides, that you have information on theta, but you want to gain insight on y. So a nice result, I think, is that if M is invertible, if it behaves nicely, and if it's differentiable and invertible, because it implies differentiability, then the order in which you combine the distributions or you transform to get a distribution, an induced distribution on y, it doesn't matter. But this is not always the case, as we shall see very shortly. So this is a simple example that is useful in real life that is not invertible. So what we have here is a simple epidemic model that is called the SIR model, and the quantity of interest of this model is R0. R0 defines whether there's going to be epidemics, the epidemic is going to progress or not in this context. So usually people have their opinions on beta and gamma, the two parameters, the infectivity and recovery parameters. So what you can see here is the dashed lines are the distributions for each expert, and the solid colored lines are the pool distributions. And I think you agree that the pool distributions, they achieve a sort of a consensus. But the interesting thing about this is that if you pool first, if you combine the distributions and then you transform to get an induced distribution, if you do this, then the distribution on R0 is really nice looking. It's a gamma rated distribution, and you can express this analytically. So it's nice. But if you do it the other way around, if you first transform each distribution to get a distribution on R0, and then you pool them, it looks very ugly. So ugly that I didn't even attempt at writing the density there. And you can't really express it analytically. So these are the two distributions obtained by switching the order in which you pool or you transform the quantity. And you can see that they are different. They indeed are different, which is a very surprising, I think, a surprising result. And I really don't know in which order we should do these things, if there's a right way to do it. Computer's a bit slow. All right. This is not the final slide. Okay. So thank you for listening. All the necessary code and the manuscript are available through GitHub in this repository, and the slides are going to be available too. The slides are available, but they're going to be available through the conference, and I invite you to look at our code, and we are always open to contributions. Thank you very much.
So we have plenty of time for questions. Questions? No.
So the pool and induce or induce and pool. So why are you surprised when you get different answers? I mean, you start with equation 1, and on the first slide.
Yeah, let's see if we can get that.
And as far as I can tell, I mean, that's a statement of, that's a model. You've chosen a model. You've chosen a specification of a distribution conditional on these Fs. And theta is specific, and so it's a model on that parameter, or that set of parameters. Not for other things. So not for non-invertible transforms of theta. It doesn't marginalize. The functional form on any margin in theta is not of the logarithmic pool form. So it's a specific model specific to a particular random quantity theta. So I mean, am I misinterpreting? Is there something deeper here that I'm missing? Because I wasn't surprised when you got different answers with different transformations.
Yeah, I think I can speak here. So, yeah, I mean, I don't know. I wasn't expecting this. I was expecting that, you know, I can't tell why the operator, the logarithm pooling operator, would transform things in that way. But now that you know, with your contribution, I think I can see it more clearly. That, you know, what? Yes, yes. So yeah. So the theorem I mentioned depends on the existence of the Jacobian. So if the Jacobian exists, that is, if you can invert it, then the order is not gonna change. But in that particular example, we can tell very easily why this is not the case, because the transform reduces dimension. So it's from R2 to R. So yes, yes. So yeah. So you're absolutely right. That is a marginalization thing. It's a marginalization issue. Yeah. Thank you.
Any more questions? Okay, so let's thank Luiz again.